pass this around. You can sign up. Assuming we might get some more, I'll hand out a schedule. So you've heard the story that we meet every day that there's class, right? Or every day until around November 1st, and then we're essentially done. And there's not that much to do in the course, so far as that goes. Except come to class and read the notes. Now, the handouts you can pick up from my assistant, Jerry Hill, who's right downstairs in 4134. In fact, there's the information for Jerry. All this stuff is on the web at web.mit.edu/337. So if I wanted to focus in on that. This is new this year, so I got to figure out where my zooms are. So there's the address up there, the web address for the course, and of course there's information on myself and Jerry Hill. And there's breakfast in 4133. You guys they didn't tell you that? Nope. Okay, well you can have breakfast afterwards. There's actually plenty of breakfast. Usually we get about 20 students in this, but we usually get the 13 A's. Are they taking something else at this time, or are they just taking a lot of stuff this term? No, the other guys didn't want to come in the afternoon? Well, in any case, whatever they've decided to do. So if we, well, let me tell you what's required in the course. You can go to the website and you can see what's required, but basically coming to class, discussing things. I encourage questions. I like digressions. I'd rather digress than give what I prepared to give, so far as that goes. You have to do either a term paper, which is about 10 pages, or you have to do some homework problems, which are on the web. There's 10 problems. They're also in the handouts when you get the handouts, so far as that goes. The requirements for the course are not extensive, other than kind of coming to class. There's an overview on the website that kind of gives some of the comments from students in past years, where they say things like, the professor speaks very fast, pointed out through simple scientific analysis how different papers could be flawed. I mean, it'll give you some idea. It's unlikely you can follow everything as he goes along, so don't worry about it. This is kind of an overview course in many ways. Although I've had a number of students come back and tell me after they graduated they learned more in this course that was useful to them than most other courses. I also often say that I'll solve one differential equation just to prove I'm an MIT professor, but you know, we're not gonna dwell on the math. We're gonna talk about the physics of what's going on, trying to understand more about what's going on. The course is actually divided in two parts. Historically, 337 was a course on welding and joining, and then it turns out that Professor Masabuchi in ocean engineering used to teach a welding course for the ocean engineers. It was 13 something. And then when he retired, I was asked to add the things that the Navy program asked to be added to this whole thing. So it turns out that there's 3371. So originally there were 25 lectures in 337, and then we added these other lectures, which are fracture mechanics, material selection, welding and joining metallurgy, which I didn't cover because Professor Masabuchi used to cover that, and then non-destructive evaluation, so far as that goes. So in any case, so that's 337. There's 12 lectures there. What we do this term, if we get enough students to give the lecture live, I'll give the 25 lectures this year, and then the 12 lectures the days that I have to miss. And in fact, on that sign-up, on that schedule sheet, you'll see some days underlined. The first one's the 23rd. I have to be in Pittsburgh on the 23rd. I have to be in Philadelphia on the 1st. I have to be in Utah on the 7th and New Mexico on the 8th of October. So 12 of those lectures you'll get are going to be the 3371 lectures this year. Now, you probably signed up on the 13 number anyway, right? So I don't even remember what that number is, but it's the same course. And Professor Wiersbicki is officially the 13 person, but he really doesn't have anything to do with the course. Just have to have a professor from 13 who's officially involved. Now, for the 3371 lectures, if you're the only two or if we only have 13 A's, turns out 2 summers ago I gave the lectures to 13A students live for 3371, and I emphasized in that year on the video naval applications. Whereas last year in the fall, I gave the 3371 lectures, and I just kind of emphasized all kinds of applications, not necessarily naval applications. So I would suggest that you look at it's going to be summer 2002 or something like that, 3371 lectures. You can tell because the classroom was one over in building 5 or something, as opposed to this classroom, if you just look on the website. But in fact, if we end up with enough students, then V will actually show these in the mornings to you. Otherwise, if we don't get enough students, then I'm afraid even though you want to take it live, I may not do it for just 2 students, because I also have to teach another course on thermo at 9:30 on Mondays and Wednesdays. In any case, that's the format. The requirements are basically come to class, do either a term paper or a problem set. You can do the problem sets together as long as you go over all the problems. I've had as many as 19 students turn in one problem set with 19 names, okay? But it means I have to grade fewer problems. But you can work together as long as, well, let's say you had 10 students and you divvied up one problem per student, as long as you get together as a group and everybody discusses every problem. I don't care that you actually go through the pain of solving the problem yourself, as long as you understand the problem. In fact, the only reason I even require the problem set or the term paper is because MIT requires me to grade each student individually, okay? Basically, this course is one it originally wasn't required for anything, and I basically turned it into one where I just try to pass information on and don't worry about all the rigmarole that goes with all the typical academic teaching, right? So any questions on the administrative stuff? Okay. So one of you were in Japan the last 3 years? What part? Yokosuka?
Actually, Sasebo.
Sasebo, okay. And where were you?
I've been overseas too, in Italy.
Okay. I lived in Tokyo with O&R back in the mid-'80s. So anyway, so I remember good old Japan. Okay. So why study welding is what we're going to talk about a little bit today and give you an overview of the types of things that we'll cover in the course. Well, first of all, it's integrative. It uses, and by the way, there are notes for all this stuff for the lectures online. In years past, I found a student who would come with a laptop, and I'd single them out and say, okay, I'll pay you to make extensive notes, and we'll put them on the web. So you can make notes if you want, but you don't have to. All this stuff is on there. I've been told it's the most complete website of any course. That's because I get various students to help with it each term. In any case, it's integrative in that there is not a engineering discipline of welding. Welding involves some civil engineering. If you're talking about welding bridges and buildings and things like that, it involves mechanical engineering. It involves physics, chemistry, electrical engineering, metallurgy. It brings all these things together, and in fact, that's one of the reasons that it's always been an exciting or interesting field for me, because I can work on anything I want. We can talk about plasma physics and how fluorescent lights work, okay, because that's electric arcs. You can talk about lasers and electron beams. You can talk about surfaces and cleanliness for adhesive bonding. I mean, you name the topic, and I can probably find something that has to do with something. In fact, Nowadays, there's even biological things, as people are looking at ways to, you know, replace sutures and things like that in repair of the human body. They basically have to join blood vessels together. And so there's some of the same science that's involved, maybe modified a bit because it is organic human living tissue as opposed to inorganic things. But anyway, so that's one of the reasons to do it. It has improved the size, cost, and reliability and lifetime of what we make. Can you imagine building some 8-inch thick pressure vessel by trying to rivet it together? I mean, it couldn't be done. If you just take, in your case, the size of ships. I mean, the first ships, of course, were wooden and stayed with that until, you know, 150 years ago. They started to come out with some other ships, and they were riveted. It really wasn't until World War I that they started to try to weld ships. And they only welded part of them, but they had a huge shipbuilding program. And in fact, Comfort Avery Adams, who was the founder of the American Welding Society in 1921, started the American Welding Society, 1921 or 1919, anyway, because he was a professor of electrical engineering at Harvard, and he basically, during World War II, he was in charge of, I think he was either on or he was chairman of the Emergency Fleet Committee, because they all of a sudden, in 1917, they had to build a bunch of ships to get the boys over there. You couldn't fly them over. You had to have troop transports. And welding, which had started, arc welding, which kind of started in 1880s when Edison and Westinghouse finally provided the world with a kind of a universal source of electricity, because you had to have Edison and Westinghouse build the generators and stuff. People started doing arc welding, but the quality of arc welding wasn't very good, and people didn't really know how to design. Most of those ships were still riveted. The Titanic, which was a few years earlier, was all riveted. And if you read any of the stories about why the Titanic collapsed, or why the side of it collapsed, some of it's brittle steel, but some of it was the rivets, okay? You just kind of ripped great big gashes. And then the first really major critical structure for arc welding was probably in the early 1930s. During the Depression, they built a gas pipeline, and they called it the Big Inch. It was a 30-inch pipeline from Louisiana up to New Jersey. So it was a gas transmission line, and you don't like those things blowing up. They do blow up actually about half a dozen times a year in the United States, but you don't really read about it because it usually just burns up some farmers' cows. Every now and then, like 10 or 15 years ago, one blew up in Edison, New Jersey, and it was real exciting when you have 600-foot flames shooting up in the air. But that's a critical application. The real growth of welding was really World War II and all the Liberty ships and things like that. But then you get into the fracture mechanics, because they had these Liberty ships falling in two in the middle of the North Atlantic. And so after World War II, there were three places that did big studies on why the Liberty ships failed. And one was because it used to be the advantage of a riveted ship. If you had a crack in a plate, the crack ran through the plate and it stopped at the end of the plate. And it didn't go into the next plate because there was nothing to transfer the crack. When you weld everything together, the crack could run all the way around. And that was one of the problems. But then they learned about brittle fracture. And the three places they really studied were one called the British Welding Institute. After World War II, a guy named Richard Weck got on his bicycle. He was at Cambridge University, and he kind of pedaled out in the countryside, and he found this area outside of Cambridge and got some money from the government. And he started the British Welding Institute, which is now one of the world's premier places to study welding. Another place was the Naval Research Lab. A guy, Bill Polini, was a scientist there, and he actually, with lots of U.S. Navy money, developed a lot of the tests that we still use today. The Navy still uses some of these tests. The explosion bulge test, if you've ever heard of the explosion bulge test. And the other place that did a lot of work on all this happened to be right here at MIT with Professor Morris Cohen and Ben Averback and a few others, trying to understand the causes of brittle fracture. And anybody know the difference between strength of a material and fracture of a material, or the criteria that we ended up. I mean, starting around the 1880s, people were just, civil engineers learned how to pull tensile specimens, right? And understand the strength of a material. And around 1950s, it wasn't the force that a material could withstand, it was the energy it could absorb. So the difference between strength and toughness is just force versus energy, okay? And a lot of people don't kind of put it down quite that simple, but that's all it is.
Is that what the impact test is for?
The impact test, you're measuring the energy that it can absorb. You drop something on it, and you see if it breaks, and how it breaks. How much energy can it absorb? And in fact, in the 3371 part of this, I'll do some plots of, actually they're Pellini plots originally, where you plot strength on the horizontal axis and your vertical axis, you put toughness. And they're called ratio analysis diagrams. And that's a different part of the course, but it is part of the course to talk about those and talk about what limits you can get in different materials for strength, this combination of strength and toughness. So in the 1880s, we learned to build structures, and they would pull tensile specimens and make sure they had the right strength for the structure. In the 1950s, we learned, because of World War II and Liberty ships, that you needed toughness as well as strength. And it was the combination of the two. In 1990, when they had the Northridge earthquake in California, they learned that you need toughness in the building industry as opposed to the shipbuilding industry, okay? The construction industry. They never had a toughness requirement because there was no dynamic load to a building unless you had an earthquake. But when you had an earthquake, guess what? You have a dynamic load, and you need energy absorption, okay? So for the last 50 years, these toughness requirements have been evolving. Things don't really move quite as fast as we like to think. So anyway, it's improved the size, it's reduced the cost considerably, and it's improved the reliability in life. It's ubiquitous. Well, what do I mean by ubiquitous? What does ubiquitous mean? Anybody know? Ubiquitous means it's everywhere, okay? Welding and joining are everywhere, and one of the things I usually say at this point is, think of the largest standalone manufactured product. By standalone, I'm not talking about some great big forging, because the forging by itself is just paperweight. You have to use it in something or some great big casting. The largest standalone product that doesn't contain a joint. No, you can't, it's not a chair, it's not a desk. In fact, it has to be a monolithic material. If you make it out of two different materials, like those chairs where you got a cloth back, and there's got to be a joint between the cloth and the plastic, right? So if it's not a monolithic material, so it also actually has to be a monolithic material. And 20 years ago, when I first started asking this question, people would say, well, a nail, or a pin or something. And one person said a cast iron frying pan. But you have to say cast iron frying pan, because if you said an aluminum frying pan, they don't make those handles out of aluminum, right? They make it out of plastic to aluminum, and there's a joint there. It may not be a weld, but it's a joint. You can even argue that a milk bottle's got a joint because you got to seal it at the top. If you have to open something up, there's probably a joint there. So it's got to be a monolithic material. So I said this once about 15 years ago at a workshop at one of the national labs, and his MIT professor, who's retired now, and that really bothered him for the next couple of days. And he came back to me about a week later. He said an anvil was the largest thing he could think of, okay? Now, there's some pretty big anvils. There's some anvils almost the size of this room, which you use in forging presses, okay, great big forging presses. But basically, if you start thinking about virtually anything you want to look at, there are joints somewhere. Even this molded plastic cart, the tubes and the table have joints. Now, why is that important? Well, we'll get to that. Actually, another reason why you want to study welding is it's a large fraction of the manufacturing cost. Joining usually comes at the end of the process where you've made all the subcomponents and you're going to put them together. And if you screw it up at that point, you just lost all the prior value that you added in your value stream. So it's a relatively large fraction of the manufacturing cost. So those are some of the reasons that you might study welding, all the positive reasons, let's say. The negative reasons include the following. One is there are many failures that are attributed, oops, I can't read it, to welding. I often say back in 1986 I bought 2 cars within 1 year, and I had like 7 warranty repairs, which is kind of typical if you're buying U.S. cars in the middle 80s, and every single one of them occurred at a joint. In fact, I remember as a young new professor here, one of the graduate students told me that Professor Plou, who's retired now, but was telling his fracture class that something won't fail unless it's been welded. Okay, Professor Russell said, or cast. Okay, well, there's a reason why things fail at welds. One is we usually put the welds at the most highly stressed locations. We put it at the corners where the stress concentrations. Okay, we put it where there's a change of geometry, just because it's cheaper to make the part that way. You take one part of one geometry, one cross section, another part of another cross section. You want to join them together. You're going to put them at the stress concentration. Another reason is there's lots of cases where the welds are not as strong as the surrounding material, and therefore they are weaker, and there's always that challenge. They're talking about steel, right? And they were talking about mild steel. They weren't talking about HY80 or HY100 or HSLA 100. They were talking about mild steel, okay? And that's absolutely true. It turns out mild steel weld metal, if you're talking about 35 or even 50 KSI yield strength steel, the lowest strength welding electrode you can buy is 52 KSI strength. It's E6010 electrode or E6011 electrode. It's 60 KSI tensile strength, 52 KSI yield. So anything that's 36, A36 is a standard constructional steel, 36 KSI. Ship steel, EH or the D32 or anyway, these are commercial ship steels, which a lot of your, the types of ships you're getting off and putting into the commercial fleet, that you're now, you're only building warships primarily now. You're not as building as many of the others, but a lot of the others have D32, DH32, whatever. I can't remember what the commercial designation, but it's a 50 KSI yield steel. It's a high strength steel. Shoot, I think the Nautilus, wasn't it made out of 50 KSI yield steel, if I remember? Are you both surface? Okay. But I think the Nautilus in the 50s they had gone to 50 KSI yield steel, and that was a big deal. And it's absolutely true that it's hard to lay down steel weld metal that doesn't have at least that kind of strength. Now, if you get up to HY80, it's not always true, okay? So your maintenance guys, the chief who said that to you or whatever, he's just used to repairing the garden variety steel.
HY80 they had on the ships was like the shear strake or something like that. I mean, everything else was just standard steel.
Right.
Maybe aluminum.
Well, standard steel, it was probably 50 KSI. I mean, they don't use A36. They do.
There wasn't anything exotic about it.
Yeah, well, that's because on surface ships, you're deflection limited. You're not strength limited. You've got to make it about 3/8 of an inch thick metal, or the thing's just going to buckle on you. Yeah. Okay, so you're deflection limited. Of course, now the big thing is they want to make aluminum ships, right? Because of the littoral battlefield and all that other stuff. Okay. Actually, they've talked about composite ships, and we'll talk about that in a little bit. Types of failures they have. The Alexander Keeland was an offshore oil platform. Oops, I got to figure out how this works here. Okay, so the Alexander Keeland was an offshore oil platform that was built, in the 70s at a French shipyard. The thing here is, actually Alexander Keeland was 1976. So you got an offshore oil platform, and in fact there was a little hydrophone or sonar bracket that was welded on to a little piece right there. So you got these legs are probably 10 meters in diameter, and these guys are probably only a meter or two in diameter. And then you got this little 1 foot wide thing. It was a bracket, basically a flange for a sonar. It was supposed to have a sonar instrument attached to it. And it turns out in the French shipyard that built this, they, well, maybe I didn't show all that. Okay, here. Okay, so here's the little thing, 325 millimeters across. Okay, about a foot, a third of a meter. They had a maintenance department, and they had the shipbuilding department that built the main structure. In the shipbuilding department, they were used to using higher strength steels and keeping all the materials segregated and stuff. The maintenance department was just a maintenance department, and it was kind of the same attitude. You can weld anything with anything. And they had the job of putting on this little attachment bracket, and it turns out they just went and got a piece of pipe out of the storehouse, and it turns out the piece of pipe was medium carbon steel, not low carbon steel. And because medium carbon steel is harder to weld, it turns out they got a little crack that ran around and eventually ran around the whole leg. And I think 178 people lost their life in a storm. But there was a little weld right here where they welded the whole thing together, and the fatigue crack grew all the way around. There was a big national investigation in Norway back in the 80s to look at why the Alexander Keelan collapsed. And it was a pretty dramatic failure. And there's plenty of other failures that occurred due to welding. One of the problems with welding, is it's often applied as an afterthought. A designer designs something and they never figure out how you're going to actually stick the parts together. Now we're getting better at that, but 20 years ago that was a common problem. Designers never worried about sticking it together. They just always figured that the people in the joining group would worry about that. And they would, it's sort of like the people who designed automobiles. You don't remember it because you may not have even been born at the time. You probably weren't. But back in the 70s, Ford designed a vehicle, or was it GM? I can't remember. One of them designed a vehicle. You had to lift the engine off its engine mounts in order to replace one of the spark plugs. Okay? I mean, you know, when they were working on just the engine without the rest of the vehicle around, it was easy. Okay? And someone else fit the engine into the vehicle, but no one ever bothered to figure out what the clearance was for that it was a four-cylinder engine in a small vehicle. And it was ridiculous, you know. It cost a fortune to change your spark plugs. And back then, you didn't have 100,000 mile spark plugs, okay? One of those types of things. It's often an afterthought of how are we going to do this? Or another problem, well, it's often performed manually. And so you have variable quality. And there are lots of problems. It's not the most pleasant job in welding. Some people think it's great, but there's lots of people who don't want to go down into some little area. I know in one aircraft, they call one area of the aircraft a hellhole, because you basically have to be a small person and wind your way in there. And I'm sure you've seen some things like that on ships, okay? They are very complex processes. When we get down to try to understand them, I learned early on that the reason the physicists didn't want to study welding was not because they would say, oh, that's already known, or that's not an interesting problem. The reason it wasn't interesting is because it was too hard, okay? You can't simplify things in a nice little box. Theodore von Karman, who was kind of the father who had explained why the Wright brothers were able to fly, he was the father of modern hydrodynamics and aerodynamics. Theodore von Karman said, a scientist explains that which exists, an engineer creates that which never was, okay? So the scientists like to simplify the problem so it's one that they can solve mathematically, that they can understand everything they can about. An engineer actually has to go in and solve a real problem, okay? And it's a different type of thing. Welding is a real problem. Few people are educated in welding. It turns out that in this country, we graduate about 30, maybe 40 or 50 welding engineers in the whole country. People who actually were educated to be a welding engineer. In the former Soviet Union, they educate about 5,000 a year. Well, that's a lot of political reasons for that. One of which was that the Patton Institute in Kiev, Boris Patton made his name in Russian or Soviet history by repairing the tanks in World War II and getting them back to the front against the Germans. and he was welding these together. And he started an institute. His son took it over. Boris Paton, his son, is probably well into his 80s, maybe 90 now, but he still runs it. And Boris Paton, the younger, was one of the members of the 7 senior members of the Supreme Soviet Academy of Sciences, or whatever they call it. Well, those are the people who divvied up all the research money in the Soviet Union. And then when it got to Ukraine, where Kiev is, he was head of the Ukrainian Academy of Sciences, and they divvied up all the money there. So all this money went to this huge institute in Kiev, and so they did a lot of work on welding. And because of that, the Soviets were able to do things like build an alpha titanium submarine, because they had spent, I estimated, a factor of 10 to 50 times as much in developing technologies for joining titanium, because they had a completely different economic system. I mean, our businesses would have to justify making a profit. They didn't have to do that. If their admiral said, we'd like a lighter weight submarine, you go off and put 1,000 people on developing technologies for joining heavy section titanium. You know, the U.S. Navy had 5 or 6 people studying it, when the Soviets had hundreds, okay? And so they developed the technology. We could build a titanium submarine today if we wanted to pay for it. It wouldn't be cheap. And if it really gave us the types of advantages as a system that everyone thought it would give. Well, back 25 years ago, maybe it did give certain advantages. It could dive deeper than we could go. It could go faster than we could go, even on the surface, and go faster underwater, supposedly. But those things are not the things we're interested in now. I mean, they'd love to build, they'd love to build a titanium surface ship if they could afford it. Okay, so this whole question of cost, that's another part of the course in the 3371 part. But anyway, few people are educated in welding, and typically what happens is a company will hire an engineer. They'll run into some problem, whether you're Ford or General Motors or Boeing or Rockwell or whatever. They run into some joining problem, and the manager tells some physicist or some mechanical engineer, says, you're now a welding engineer. How did I become a welding engineer? I went to work for a steel company that said, you're a welding engineer. I'd never welded before. Right? I took part of a course here at MIT, but that was next to useless. Okay? So people basically have to pick it up on their own, something you pick up off the street, sort of. Okay? The ability to join a material limits its usefulness. We still have some problems joining heavy section titanium. We have problems joining light section titanium. I've got a lot of parts here that will show you some of the types of things that we do join. And maybe you have any questions on any of this stuff? I'll give you some example. Here are some pictures of some joints that were dug up out of the Boston streets. That is a cast iron, they call it a bell and spigot. This is the bell and this is the spigot that goes inside it. And they pack it with oakum. And this was a gas main. Okay. Here's another gas main a few years earlier. Let's drop that down a little bit. It's a little too intense. Oh, there we go. When they're digging up the Boston streets, they find these things. And that's basically just a tube within a tube, a larger tube, and there's the end on of that. And then you can still see they just kind of pack some kind of gunk in there. Here's another, and you can see the gunk on the side of that, inside that. But before that, and I didn't get a picture of that, anybody know what they used for gas mains? And these were gas mains to basically for street lights before Edison and Westinghouse, right? Wood, exactly. They used to just take big logs and they would gun drill them. You know what a gun drill is? Well, it's a long drill, but in a gun drilling operation, the problem is these long drills get to be fairly slender and they will tend to bend. And so what you do is you counter-rotate the part that you're drilling, and that way you can drill a long straight hole in a gun drill. And they call them gun drills because that's how they used to make gun barrels many years ago, is by gun drilling them. And gun drilling is basically two counter-rotating a drill that rotates clockwise and a part that rotates counterclockwise, for example. So they used to gun drill tubes. And so now sometimes when they're digging up the streets of Boston, they'll come across one of these old logs. And the log might be an 8 or 10 inch diameter log with a little 1 inch hole in it. Okay? And that's how they pipe and they would have joints there. They just kind of caulk them up with some goo to protect them. Other joint, well, we've changed gas mains. Now, we started screwing together pipe for small diameter pipe, larger diameter pipe. We started welding in the 1930s. Today we use plastic pipe. Still has to be welded. Okay, it's a hot plate welding process. In this case, they basically put a heater in between the two. They kind of have to hold it there for 4 or 5 minutes as the heater in between these two pieces. The two pieces are separated. Two pieces of pipe are separated, and they bring the two of them up to this little circular heater. Hold them there for 4 or 5 minutes. Why? Because the thermal diffusivity of plastic is not very good. It takes time for the heat to get in there. Then they pull the heater out, and they have a tool that squeezes them together, and you get this flash that rolls out. And you also get some residual stresses. I put this up here. Let's see. If you look carefully on here, you'll see that the thing is not. This thing kind of tapers in. It was expanded when it was hot, and it's got residual stresses as it cools down, if you want to look at that. And one of the problems is those will sometimes fail by a brittle fracture because you really haven't done anything to make a true strength weld, because the long chain polymer molecules don't really cross that boundary. You created a joint, but that joint is just kind of where they stuck together. And we're going to talk about how you make a joint like that, and how you have to get rid of any surface contamination.
The outside temperature affects something like that. I mean, if it's cold enough to crack.
Well, it's buried in the ground.
I mean, but if the ground, say they buried it too not deep enough.
If you don't bury it deep enough, you got serious problems. In Massachusetts, you go down 2 feet, and it's always 55 degrees. In fact, if you go through like Williamsburg or something, they'll have root cellars in the back of the houses, okay? If you go down about 2 feet down in Virginia, it might be 55 degrees, it might be 50 degrees in Massachusetts. You know how you determine the temperature of the ground several feet down? It's whatever the average temperature is in that part of the world over the whole year. Because if you just go through the thermal diffusivity equation, the distance heat travels, this is something we'll go through in the course, is proportional to the square root of the thermal diffusivity times time. So the distance heat travels, and a typical thermal diffusivity for something like dirt, soil, rock, is probably something on the order of 0.5 centimeters squared per second. And I can multiply that times T, and I can square all this, and I get 25 times 10 to the minus 4 times T equals x squared. Okay? So if I take, did I get that right? I think I got that right. So T, well, let's see, which one do I want to do? Well, and a year is 8,000 hours, which is roughly 10 to the 8 seconds. I'm just going to round some things off. So 1 year is 10 to the 8 seconds. And I now have 25 times 10 to the 4th. And if I take the square root of that, I get 500 centimeters, okay, which is 5 meters down. Did I just do all that right? We might have to check that later. But actually, what I gave you was for solid if it was rock. If it's soil, it may be 1/100th of that, because you got all this, air insulating. Half of it's basically space in between the particles. But in any case, the depth, we know the freeze depth In the winter, it's only about 6 inches around here, 12 inches. And that's a 3-month freeze cycle. And since this goes as the square root of time, over 12 months, you only go twice that depth. Okay, is one way to think of it. So if I freeze down to 12 inches in 3 months, in 12 months, I'm only going to freeze down to 12 inches, or to 2 feet. So if I go below 2 feet, what am I doing? The ground is basically just seeing the average temperature over the whole year. If I go down 5 feet, I'm seeing the average temperature over the last 50 years, or something like that. And so, yeah, on the equator, root cellars don't work very well, but up here you get the average temperature of the whole year, which is maybe somewhere in the 50s, low 50s. So if you go down very deep in the ground. So it won't freeze. Now if you go up to the north slope of Alaska, you got permafrost that goes down 1,000 feet. Because what's the average temperature over the last million years? Okay. So once you get below the first foot or two of the soil, heat transfer tells you that you're just seeing the average temperature over the year. So they bury it in the ground. But you're absolutely right. If that is not protected, in fact, up in Nome, Alaska, they built some, Barrow, Alaska. They have all the oil money, and they built. They wanted to have flush toilets, and they spent $400 million for 1,000 people because they had all this oil money in Barrow, Alaska, and put in something like 10 miles of this heated chase just to be able to run piping from the town out to this cesspool, which they basically just dump it onto the tundra and let it freeze. Okay? Because what else are you going to do with it, right? But they wanted to have flush toilets, just like the people down in Anchorage. Okay? But up there, the ground is always frozen, and you couldn't run water unless you actually heat it. So they have to heat this 10-mile corridor. They call them, I can't remember. Anyway, they call these big channels, and they do all their piping through this one channel. Okay, it's ridiculous. They couldn't do it if they didn't have all the oil money. So where are we? So that's the plastic pipe. What else do we want to talk about? This is a piece of tantalum tubing. Okay, lots of the tubing or pipe that you buy is welded. I just happen to bring this. Tantalum is used because of excellent corrosion resistance, so it's used in the chemical process industry. It's one of the only things that will stand up to boiling hydrochloric acid, for example. And I just happen to have a piece of welded tantalum tubing. This is a piece of this basically holds some little gears as part of a transmission or something in a GM car. In this case, it's just a little welded steel cage, but in order to have anti-galling properties, they coated the surface with an aluminum babbitt. So it's basically a bearing material. And so they had to bond the aluminum to the steel, and they do that in a roll bonding operation. That's a joining technology. If you want to build, you golfer, okay. If you want to make metal woods, how do you make a hollow metal wood? Well, you cast a hollow piece like that, and you cast a cover on here. You put the two together, and you run a weld around it, and then you sand it down, and it looks nice after you've sanded it. Okay, but that's another technology. If you want to make, this is a test piece for the F-22 jet engine, and this is a diffusion bonded piece of titanium for an airfoil. This is just a laboratory specimen. They cut it, but this would have been a great big vein that they used. So that's an example of diffusion bonding. This is actually a weld that I made more than 25 years ago. First contract I ever had, the Navy was interested in building heavy section titanium, so that's a submerged arc weld in titanium. This is a piece of the X-33 spaceplane hydrogen tank. In this case, they wanted to make a very lightweight structure. They had something about twice the size of this room. It had 5,000 gallons or whatever of liquid hydrogen. They tested it at NASA Huntsville, and this is a graphite epoxy composite on this surface. There was supposed to be one on this surface. This was kind of a Kevlar. It's actually Nomex. The Nomex suits for the firemen and things. Nomex honeycomb. Very, very lightweight. Composite structure, adhesively bonded. Problem was the adhesive joints were no good, and when they tested it, one of the skins just peeled off, and they ended up canceling a $1.3 billion program. That vehicle was supposed to be the prototype vehicle for the vehicle that was going to replace the space shuttle.
Bond right here?
Now the bond was actually the bond is still right here. Okay, they had sheets of adhesive, so they would buy this honeycomb off the shelf from one company. They would put a sheet of epoxy plastic, kind of like a big piece of, saran wrap, and then they would wrap the composite fibers on there, and they'd have to put the whole thing in a big autoclave, and they used the largest autoclave in the Western world, which was in Sunnyvale, California, and that was the limit to the size of the vehicle they could build because they were using the largest autoclave. It was lousy bonds on the adhesive. We might talk about it later, but that's a very lightweight. The whole structure was the size of a two-story house, maybe a couple thousand square foot, two-story house. It only weighed 4,000 pounds, about as much as a Ford Explorer, and it had all these titanium and Inconel ports and things on it too, for where the hydrogen went in, the valves and stuff. So the structure was very light, but the cost was $50 million. So you're talking $12,000 a pound fabricated. So it's light, but it's expensive. So when I hear people say, well, we're going to build a ship, a littoral battlefield ship that's going to go at 70 knots and all this other stuff, and we're going to make it out of composites, I say, sure. Okay? And how are you going to repair it? That same chief that tells you that, you can weld anything, right? How's he going to repair that, right? So there are lots of issues there. In any case, that's the end of today. We will be here tomorrow. We'll see if we get any other students and decide what's going to happen.
So, we've had a lot of experience with this in yacht manufacturing, American stuff, with the
Yep.
aircraft. Why were they having such trouble with the bonding in the Nomex and the
Well, in this case, it was the largest such structure that anyone ever built. And it turns out they were on it gets to be very political. They were on a fast track schedule. NASA decided they wanted to prove rapid prototyping, which was sort of the thing that the military came up after the first Gulf War. They wanted to do rapid prototyping. And the first design they couldn't afford. It was a ring stiffened composite with three-dimensional weave composite, the stiffeners. And the stiffeners were going to cost them, hundreds, several $100 million, and they had to build two of these tanks for $100 million. So they were behind schedule. They had to go with a brand new design. They ended up and they got a data sheet from 3M, who made the adhesive. And 3M basically, the thing said it had a 10-day shelf life. Yeah, the epoxy was stored in a refrigerator to keep it from curing. Okay, and it said at room temperature it had a 10-day shelf life. Well, fine, we'll use that because we're going to be 3 to 7 days in order to lay everything up before we get it into the autoclave. Okay, well, after the fact, if you go to the website, it says a 10-day shelf life. But if you actually look at the strength of the joint versus days, this is 1 and this is 10. Okay. The strength went from 100% down to 10% in 10 days. And so it turns out they were somewhere in there, depending on whether they had a 3-day autoclave or a 7-day autoclave cycle. And they didn't know that until after the fact. In fact, they had one of them debond when it came out of the autoclave, or in the autoclave. When it came out, they saw a blister. And they said, oh, we got a problem. They thought they had designed it with like a 300% safety factor on the strength of the joint. They went in, they actually took cores and had to do repairs on the thing and measured it, and they said, ooh, we have about 1/3 the strength we thought we had. So they sharpened their pencils, and they finally determined they had a 1.05 safety factor on the strength of the joint. They said, well, that's good enough. 5% safety factor, that's almost 300%, right? So they knew when they put it in test in Huntsville that there was a chance it was going to fail. Pretty good chance it might fail. And they put it in, they loaded it up with the liquid hydrogen. Nothing failed when they had the liquid hydrogen in it. They finished their protocol, they started to pump the hydrogen out, and they all were breathing a sigh of relief. And then a half an hour, as it started to warm up after the hydrogen was out of it, a half an hour later, the whole thing had frost all over it, but they had it on a video camera, and this all the frost broke. And it turns out hydrogen leaked into those cores, which was another problem. They had gotten some thermal data, or not thermal data, but they had actually built at the Stennis Space Center in Mississippi. They had built for the Delta III rocket program, they had built a little prototype hydrogen tank out of the same stuff. And the Lockheed Michaud Space Division was supposed to get the contract to build the X-33 space plane. But when the Lockheed Michaud Space Division saw that NASA wanted a 33-month schedule, they said, you can't do that. It's impossible. So they refused to bid on it. Lockheed Martin's management said, well, if you won't do it, we'll get the Skunk Works to do it. So the Skunk Works bid on the $1.3 billion contract, and they got it, even though Michaud was the one that was supposed to get it, but Michaud said, we're not going to bid on something that can't be done. And so there was politics there. So the Skunk Works took this 33-month project, and they go down to Stennis and to Michaud division, and they say, well, what parameters should we use for the permeability of hydrogen in here? And they gave them a number, okay? And that's what they used as the design. And they actually tried to check it. The Skunk Works, to their credit, actually sent some samples out, and they got some results back that were clearly bogus, okay? The people who had tried to do the test under contract for them had a leak in their system on one of the seals around the thing, and so the results were garbage. And they didn't have time to redo the test. So they just assumed that they could use the Stennis numbers, the Stennis-Michaud numbers, for the permeability of hydrogen through that graphite composite. Sorry. And after the failure, the Skunk Works and NASA went back to Michaud and said, where'd you get this number? And now, 3 or 4 years later, they're still waiting for the answer. Apparently, Michaud probably just made the number up. They didn't know how fast the hydrogen would diffuse through. Turns out when you cool that epoxy down, you get microcracks when you get down to liquid helium temperatures. And the hydrogen just went in there through microcracks. They believe that they actually got liquid hydrogen into those cells. And so the thing worked just fine when it had liquid hydrogen in it. You take the liquid hydrogen out, and the liquid hydrogen inside those cells starts to expand as it warms up, and you had enough pressure to blow the thing apart as it's warming up. And the fix would have been to use a honeycomb that was perforated, so you would have an area to escape. And I remember going to the Skunk Works and talking to the engineers. They had shut down, and I saw the remains of the plane. But NASA shut them down, and they were trying to get the Air Force to pick it up, but they wouldn't. But they said, "Oh, we can do it. We can make this plane fly." And their solution would have been to perforate the cores. Okay. So you had an escape gas for the hydrogen. Long-winded answer, but it was complex. Okay. However, not so complex as it's not something that you wouldn't have expected when you'd run a fast-track project and no one really knows if something's going to work or not. Right?